Welcome to Spring LIB.
In this exercise, we're going to be talking about radius of curvature in circular motion. So I'm going to briefly review the concept. Consider that we have an arbitrary curve, like this one in blue here, where the vertical axis is the y-axis and the horizontal axis is the x-axis. And we want to know the radius of curvature of the curve at a certain point, let's say this x0 here. What should we do in order to find the radius? Well, we can use this formula here, that r, the radius of curvature, is equal to 1 plus dy dx squared to the 3/2 divided by the magnitude of the second derivative of y with respect to x. Okay, so this is how we calculate the radius of curvature of an arbitrary curve. And second, we also have to talk about circular motion. So consider that we have a particle that's undergoing a motion around a circle. So we can decompose the motion, the acceleration of the particle into two components. One of them is a centripetal acceleration that points towards the center of the trajectory, and the other one is a tangential acceleration that points tangentially to the trajectory. The centripetal acceleration accounts for the change in direction of the velocity and is equal to v squared divided by r, while the tangential component accounts for the change in speed and is equal to the derivative of the speed with respect to the time. So what we have in our problem is a block, actually a sack, that has a mass of 8 kilograms and is sliding in a surface that is shaped like this exponential here. So the surface is such that y is equal to 0.2 times the exponential of x. As I said, the mass is 8 grams, and when y is equal to 0.2, the velocity v is equal to 1.5 meters per second. Okay, our goal is to find what is the normal force that the surface exerts on the sack when y is equal to 0.2, and also we want to know what is the rate of increase in the speed in the same instant. Now notice that when y is equal to 0.2, ex is equal to 1, because y is equal to 0.2 times e to the x, meaning that x is equal to 0. So really what we want is to find these quantities when x is equal to 0. So what I'm going to do is to draw a force diagram on the block. So this here is the block. The forces, and this is the surface. The forces that act on the block are the normal force that act perpendicularly to the surface and a gravitational force that acts downwards. Okay, at any point, the trajectory of the block can be considered locally circular. Okay, so what I'm going to do is to decompose the block's the forces that act on the block in a radial component and a tangential component. Okay. Now, in order to do that, notice that if this here is the surface, then we can find the angle, this angle theta here, by realizing that the tangent of theta is equal to the derivative of y with respect to x. That's the very definition of derivative. Now notice that the normal force is perpendicular to this line here. So this means that mg makes an angle with the normal force of theta. Okay, so now we can decompose in r and theta coordinates. So in the r coordinate, we have the normal force n minus mg times the cosine of theta. And this is equal to, according to Newton's second law, this is equal to the mass times the acceleration of the particle in the r direction. Now notice that the acceleration in the r direction is the centripetal acceleration. So this is v squared divided by r. Also, in the theta direction, we have mg sine theta, and this is equal to the mass times the tangential acceleration. Okay, I'll take the first equation and realize that we want to find n. So I'm going to isolate n. So we have that n is equal to mg cosine theta plus v squared over r. Now notice that we still don't know what theta is when x is equal to 0. Neither do we know what r is. So those are two things that we need to find out. Okay, so first I'm going to use this equation here, that the tangent of theta is dy dx. Now remember that y is 0.2 e to the x, meaning that dy dx is also 0.2 e to the x. Remember that the derivative of the exponential is the exponential itself. And if we calculate it at x equals 0, we have that dy dx is 0.2. Also, and this is going to be useful for us when we're calculating the radius of curvature, the 2y dx2 is also 0.2 e to the x, which calculated at x equals 0 is equal to 0.2 as well. Okay. Now, notice that 0.2 is equal to the tangent of theta. So we can take the arctangent of theta, the arctangent of 0.2, and this is equal to 11.3 degrees. Okay. So now we have theta. Another thing that we need is the radius of curvature r. So let's find this. Remember, according to the formula that I wrote before, r is 1 plus dy dx squared to the 3/2 divided by the magnitude of d2y dx2. Okay. So this is 1 plus 0.2 squared to the 3/2 divided by 0.2. So r is equal to 5.3 meters. Okay, this is the radius. This here is the angle. Now we have everything that we need in order to find the normal force. So the normal force is equal to m, that's 8 kilograms, times g, which is 9.8 meters per second squared, times the cosine of 11.3 degrees, plus v squared, that's 1.5 meters per second squared, divided by the radius, which is 5.3 meters. So the normal force is equal to 80.3 newtons. Okay, this is the normal force. And now we have to find what is the tangential acceleration. Because remember, the tangential acceleration, as I said here, is the rate of change in the speed of the particle. So if we want to find dv dt, that's actually paramount to finding at. So let's use the equation for theta. So we have there that mg sine theta is mat. So at is equal to g sine theta. So this is 9.8 meters per second squared times the sine of 11.3 degrees. So the tangential acceleration is equal to 1.982 meters per second squared. And this is equal to dv dt. Okay, so this concludes our exercise.